morning, friends. We discussed about the different type of the thermodynamic process: isothermal, isobaric, isochoric, adiabatic process, and also the cyclic process. Right? For this different type of the thermodynamic process, we are interested to calculate the work done. How much work done is obtained for different type of the thermodynamic process. For that purpose, first we obtain the work done for the isothermal process. Right? What is the isothermal process? The question is asked like this way. That is the most important question. And what are the equation we derive for the work done of an isothermal process? That is the most important for the numerical and also the MCQ type question. Clear this thing? Okay. Now the question is asked like this way: define isothermal process and obtain equation of work done for n or in an isothermal process. Again the question is define isothermal process and obtain equation of the work done in an isothermal process. Already we discussed about the definition of isothermal process. Isothermal means the temperature remain constant in thermodynamic process. So definition is that the thermodynamic process or the process during which the temperature of the system remain constant is known as isothermal process. Again the definition of isothermal process is that the process during which the temperature of system remain constant is known as isothermal process. Clear this definition? Okay. Now the temperature is constant. So we have the equation of state of an ideal gas. So PV is equal to mu RT. For isothermal process, temperature is constant. Therefore, PV is equal to mu RT. Mu is the quantity of a gas, that means the amount of gas in mole. R is the universal gas constant, and T is the temperature of a system. But here, for isothermal process, temperature is constant. Therefore, right hand side of this equation is constant. Mu RT is constant. Therefore, we can write PV is equal to constant. PV is equal to constant. For which process? Isothermal process. Clear this thing? Okay. Now we are interested to derive the equation of the work done for the isothermal process. For that purpose, we assume that suppose an ideal gas goes isothermally from its initial state P1 V1 to final state P2 V2. Right? Again, suppose an ideal gas goes isothermally from its initial state P1 V1 to final state P2 V2. Right? Okay. Suppose at any intermediate stage, the pressure is P and volume changes from V1 to V2. Already we discussed this type of the graph. Pressure versus volume. For the isothermal process, there is the pressure P, volume is V. There is the initial state of a system I. Here the pressure is Pi, volume is Vi. And now, final state is this. Here the pressure is Pf, volume is Vf. Already we discussed about that. We bring the system from initial state to the final state in three different ways. First, we keep the pressure constant and we changes the volume from Vi to Vf. Vi to Vf. So that is the first way. We bring the system from Pi Vi to Pf Vf. Here we consider there is the P1 V1 and there is the P2 V2. There is the second state, there is the first state. Here the pressure is P1, here pressure is P2, volume is V1, volume is V2. Now listen, this graph is not important for us, already we discussed, but here to clear the concept of this, why the pressure is constant as the volume of a gas is changes from V1 to V2, or the small change occurs in volume. For that purpose, we again refer this graph. Here we do the graph of pressure versus volume. Initial state of an ideal gas is 1. Here the pressure is P1, volume is V1. This ideal gas goes isothermally from initial state P1 V1 to the final state P2 V2. Here the three ways. One is keeping the pressure is constant and we changes the volume from V1 to V2. So that is the first way. Second, keep the volume constant and make the change in pressure P1 to P2. So this way we also obtain the second state or the final state of an ideal gas. And third way is changing in both. Changing in both pressure and volume. That is the third way. So we can achieve the final state in which the pressure is P2 and volume is V2. Now here the temperature is constant. How we obtain the equation of the work done? Again, suppose an ideal gas goes isothermally from initial state P1 V1 to final state P2 V2. Suppose at any intermediate state pressure is P and volume changes from V to V plus delta V. That means we consider a very small portion of this. Here the volume changes from V to V plus delta V. Here approximate or the very small change occurs in pressure, but we consider the pressure is almost constant. And due to that reason, here we have written at any intermediate state, the pressure is P and volume changes from V to V plus delta V. V to V plus delta V. Therefore, work done in this process for this change in volume. Here the pressure is almost constant P. Therefore, delta W is equal to P into delta V. Here is okay. Therefore, the work done for small change in volume from V to V plus delta V, the pressure is almost constant. Therefore, delta W is equal to P into delta V. That is the first equation. Here, the change in volume is also very small, tends to 0. Therefore, the work done during the entire process, how we obtain the total work done to bring the system from initial state, the volume is V1, to the final state in which the volume is V2. Therefore, the total work done is obtained by taking the summation of this type of the small work done. But here the change in volume are very small, therefore this summation is converted into the integration. Therefore the total work done is integration of this type of the small work done delta W. We substitute the value of delta W, therefore integration P dV. Here we substitute the value of delta W in terms of P into delta V. P almost constant. Volume is changes from V1 to V2. Therefore, the integration has the limit is initial value of volume V1 to the final volume is V2. Therefore, W is equal to integration of V1 to V2 P dV. P dV. Yeah. Now, there is our equation 2. In equation 2, we feel that the P is constant. But no. Because from the equation of state PV is equal to mu RT. P has the relation with the temperature and also the volume. Therefore, P is equal to mu RT upon V. Mu RT upon V. We are substituting the value of P, mu RT upon V in equation 2. Therefore, W is equal to integration V1 to V2, instead of this P, mu RT upon V into dV. But mu R and T for isothermal process are constant, taken out from the integration. Therefore, mu RT integration V1 to V2 1 upon V into dV. Now here only we have to take the integration of 1 upon V. For that purpose, the standard integration of 1 upon x into dx, that is the ln x. ln, that means the base of the log is e. Base of the log is e. Therefore, integration of 1 upon x into dx is equal to ln x. But here variable is the volume v. Therefore, integration of 1 upon v into dv is our ln v. Therefore, W is equal to mu RT ln v, and value of the volume is changes from v1 to v2. There is the initial value of volume, there is the final value of volume. Now we have to substitute this value of volume. So first the final value minus initial value. Therefore, mu RT ln into bracket v2 minus v1. v2 minus v1. Therefore, W is equal to mu RT ln v2 upon v1. We have also the standard equation in logarithm. Ln a minus b is the ratio of a to b is equal to ln a upon b. Clear it? Okay. Now, W is equal to mu RT ln v2 upon v1. That is the work done during the isothermal process. Clear this? Okay. Now again we repeat up to this and then we discuss the later part. First, what is the isothermal process? The process during which the temperature of the system remains constant is known as isothermal process. Right? For isothermal process, the equation of state of an ideal gas, PV is equal to mu RT. The right hand side of this equation, mu, quantity of a gas in mole, constant, I is universal gas constant, and T for isothermal process is also constant, therefore PV is equal to constant. Now we are going to derive the equation of the work done. For that purpose, we assume that suppose an ideal gas goes isothermally from its initial state P1 V1 to the final state P2 V2. Now, suppose at any intermediate state, when the gas isothermally expands from state 1 to the state 2, at any intermediate state, suppose at this state, the pressure is P and volume changes from V to V plus delta V. And volume is changes from V to V plus delta V. This. That is the delta V. Therefore, the work done during this process to make the change in volume from V to V plus delta V, the work done delta W is equal to P into delta V for small changes in volume. Right? Here the change in volume is very small, delta V. Therefore, taking delta V tends to 0. Therefore, the total work done during entire process is. How we obtain the total work done? We obtain the total work done by taking the summation of these times the small work done for the small changes in volume. So we obtain the total work done during the entire process. But here the change in volume is very small, therefore this summation is converted into the integration. Therefore total work done W is equal to integration of delta W. Substitute the value of delta W as P delta V. Therefore integration P delta V. Here only the volume changes from initial value V1 to the final value V2. Therefore, the limit of this integration is V1 to V2. Here the P is not constant, but for intermediate state we consider the P is constant almost. But the P is depends from equation of state. PV is equal to mu RT, therefore P is equal to mu RT upon V. That is depends on T and volume of a system. But for isothermal process, T is constant, it is inversely proportional to the volume. Okay. Substitute the value of P in equation 2, therefore total work done W is equal to integration V1 to V2 mu RT upon V into dV. But the mu RT is constant taken out of this integration, therefore mu RT integration V1 to V2 1 upon V into dV. 1 upon V into dV. Now the integration of 1 upon V into dV. We have the standard equation of integration. Integration 1 upon x into dx is equal to ln x. Therefore, the integration of 1 upon V into dV is ln V. So mu RT as it is, and the integration of this, that is the ln V, and the value of volume from initial to the final is V1 to V2. That is the limit. First we substitute the final value and initial value is subtracted from this. Therefore, W is equal to mu RT ln V2 minus V1. Therefore, W is equal to mu RT ln V2 upon V1. We have the one more equation of log A minus B is equal to ratio of A to B ln A to B. We are using this concept to write down this ln V2 minus V1 in ratio form ln V2 upon V1. This is the equation of the work done during the isothermal process. Now here the two possibilities. During the isothermal process, the gas is expand or the gas is compressed. So here we have this equation for the expansion of the gas. If the gas is compressed, that means the volume is decreased. So what should be the equation of the work done? For that purpose, now from first law of thermodynamics, delta Q is equal to delta U plus delta W. Already we know that the internal energy depends only on temperature. Internal energy of the system depends only on temperature. Here for isothermal process, temperature is constant, therefore the internal energy of a system remains constant. Again, from first law of thermodynamics, delta Q is equal to delta U plus delta W. We know that the internal energy depends only on temperature. For isothermal process, temperature is constant and hence the internal energy is also constant. Therefore, the change in internal energy is zero because the U is constant with temperature. Therefore, the change in internal energy is zero. Therefore, we substitute in this equation. From equation 4, delta Q is equal to delta W. That shows that the work done on the gas by the environment and heat is released. So it shows that delta Q is equal to delta W equation indicate that the work is done on the system by the environment or the surrounding and the heat is released. That means the gas is compressed. Therefore, Q is equal to W. How much work done is equal to the heat released. Is equal to the heat released. Now our equation 3. W is equal to mu RT ln V2 upon V1. If the final volume is more than initial, V2 is greater than V1, that means the gas is expand. Initial volume is V1, final is V2. V2 is greater than the V1, it means the gas of the system is expand. Therefore, the work done is greater than 0. It means the work done is positive. It means the gas absorbs the heat and also work done by the system on the environment. Work done by the system on the environment. As a result, the volume of the system is increased from V1 to V2. So here the work done is positive. Keep in mind this case. If the final volume of a system is more than its initial volume, therefore, what's happened? The system is expand and work done is positive, and here the gas absorbs the heat. Gas is absorb the heat from the environment. And in this case, the work done by the system on the environment or the surrounding. Now second, if final volume is less than the initial. Initial is V1, final is V2. So what's happened? Gas or the system is compressed. Gas or the system is compressed. Here the work done is negative and also work done by the environment on the system. So here the surrounding compares the gas. Surrounding compares the gas. Therefore the work done by the surrounding on the system, and as a result the W is less than 0. That means the work done is negative. In that case, the gas releases the heat. Heat is released. During the compression, work done is negative. Work done by the environment on the system, and also the heat is released. It means the gas of the system is compressed. When the volume, final volume is more than the initial, gas of the system is expand, work done is positive, and the work done by the system on the environment. In that case, the gas or the system absorbs the heat. Clear this? Okay. Now for the compression. That means the volume, final volume is less than the initial volume, this gas. So what's happened? Work done is less than 0. That means the negative. Therefore, W is equal to minus mu RT ln V2 upon V1. The same equation, but here the work done is negative. Therefore, we write down the negative sign. Now, according to the law of ln, law, so we can write like this way. Ln A is to B is equal to B ln A. So here minus ln A is equal to ln A is to minus 1. We are using this concept. Minus sign mu RT ln V2 upon V1. Therefore mu RT as it is, this minus sign is the power of V2 upon V1. Right? And also we know that 1 upon x is equal to x is to minus 1. Using this concept, here the power is minus 1, therefore there is the reciprocal. Therefore W is equal to mu RT ln 1 upon V2 upon V1. It means the V1 upon V2. It is the V1 upon V2. So that is the equation for the gas is compressed during the isothermal process, and there is the expansion of a gas, the work done. So both equations are same, but here the ratio are different. Here the V2 upon V1, here V1 upon V2. Clear this? Very easy, totally mathematical. But here we should keep in mind this basic equation of the mathematics. Clear? Again, we repeat. What is the isothermal process? The process during which the temperature of the system remains constant is known as isothermal process. Okay. For isothermal process, the equation of state of an ideal gas PV is equal to mu RT, but the T is constant for isothermal process, therefore PV is equal to constant. Now, to obtain the equation of the work done, we assume that suppose an ideal gas or the system goes isothermally from its initial state P1 V1 to the final state P2 V2. Now, at any intermediate state or the stage, the pressure is Pressure is P and volume changes from V to V plus delta V. At any intermediate stage, the pressure is P and volume changes from V to V plus delta V. Therefore, the work done for these small changes, delta W is equal to P delta V. Therefore, the total work done during the entire process by taking the delta V tends to 0. So total work done is obtained by taking the integration of this equation. Therefore, W is equal to integration delta W. Substitute the value of delta W as P delta V. So W is equal to integration P dV. Now d is the change in volume. Volume changes from initial V1 to the final volume V2. So be the limit of integration. Therefore, W is equal to integration V1 to V2 P dV. Now from equation of state, PV is equal to mu RT. Hence the P is equal to mu RT upon V. Substitute here. Therefore, total work done integration V1 to V2 mu RT upon V into dV is equal to mu RT integration V1 to V2 1 upon V into dV. Now, what is the integration of this part 1 upon V into dV? So we have the standard equation of the integration 1 upon x into dx is equal to ln x. Integration of 1 upon x into dx is equal to ln x. According to this equation, W is equal to mu RT ln V and value raised from initial to the final volume V1 to V2. So using this equation, ln A minus B is equal to ln AB. First we substitute the final value minus initial. Therefore, mu RT ln final volume minus initial volume. Therefore, W is equal to mu RT ln V2 upon V1. That is the equation of the work done when the gas is expand. Gas is expand. But here, it is also possible the gas is compressed and the gas of the system achieves its final state in which the pressure is P2 and volume is V2. So we enter this equation for compression of a gas. For that purpose, we are using the first law of thermodynamics. Delta Q is equal to delta U plus delta W. Delta U, change in internal energy. We know that the internal energy depends only on temperature. Now here we are discussing for the isothermal process. For isothermal process, temperature is constant and hence the internal energy is also constant. Therefore, the change in internal energy delta U is 0. Substitute in this equation 4, therefore delta Q is equal to delta W. What it shows that the work is done on the gas system by the environment. It shows that the work done by the surrounding on the system and heat is released. That means the system is compressed. System is compressed. Therefore, Q is equal to W. How much heat is released by the system is equal to the work done on the system. Now, from this equation, if the final volume is more than the initial, there is the initial volume, final is V2. V2 is greater than the V1. It means the system is expand or the gas is expand, work done is greater than 0. That means the work done is positive. It means due to the system expand, the work done by the system on the surrounding or on the environment. And during this expansion of a system, the heat is absorbed by the system. And if V2 is less than V1, that means the gas is compressed, that means the system is compressed, initial volume V1, final is V2. Then the work done is negative, that means the W is less than 0. Here the work done by the environment on the system and during this process the heat is released. But the heat is released. Now for compression we write down the equation 3. So W is equal to mu RT ln V2 minus V1. For compression the work done is negative, therefore the negative sign is written. This negative according to this equation ln A is to B is equal to B ln A, or the minus ln A is equal to ln A is to minus A. Therefore, mu RT ln V2 upon V1 is to minus 1. This minus sign is taken as the power. Now we also know that 1 upon x is equal to x is to minus 1. So using this concept, V2 upon V1 is to minus 1 is equal to 1 upon V2 upon V1. So we can add that is the V1 upon V2. So that is the work done during the isothermal process when the system is compressed, and that is the work done for isothermal process the system will expand. Clear it? Very easy, and also the most important question. That is the most important question.